Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. Tonight, I'm going to talk about nuclear fusion. But don't worry if you don't know what it is or if you just want to understand it a little better. This is not as complicated as it sounds. We're not going to dive into complicated equations or refer to unfamiliar concepts. Everything will be explained step by step and will be easy to follow along. I will explain things like why the fusion of atomic nuclei liberates energy or sometimes consumes it, what the state of matter called plasma really is, how fusion reactions could be voluntarily produced and contained inside a reactor to provide energy one day, what fusion reactors like Tokamaks and other designs could be like, and many other things. But first, I would like to let you know that we have a Patreon page for those of you who wish to and can support this project, get more of it, and listen ad-free on your favorite podcast app. Patreon is a platform that allows you to contribute directly to our work financially. Our least expensive tier is $3 per month, but it doesn't mean you will get less. We let people contribute what they wish or can, and everyone gets everything that is on our page. Because the world is a better place when the sun shines for everyone. You will gain access to over a dozen exclusive episodes, as well as you can listen to and download all the episodes with and without background sounds. And as a token of gratitude, we offer advance releases to our Patreons. You will find a link in the description of the episode. But all you need to do right now is take a moment to prepare for our journey ahead. If you'd like, gently close your eyes and let your daily concerns drift away. Find a position that feels natural and cozy. Perhaps make small adjustments until you're perfectly comfortable. Now, draw in a deep, nourishing breath, and as you release, do it slowly. Notice how your body responds. Feel the warmth flowing from your shoulders down through your neck, melting away any tension. Let your facial muscles become soft, your jaw loose, your fingers naturally open, and your legs completely at ease. As you settle into this peaceful state, my voice will be your gentle companion as we begin our exploration together. In nuclear fission, large atoms like uranium or plutonium can become unstable when they capture an additional particle, a neutron, which makes them split into smaller atoms. This fission also liberates more free neutrons that escape from the fission atom and can participate in other fission reactions, leading to a chain reaction. The fission of atoms liberates a lot of heat and very fast particles that are ejected from the fission nuclei. This is the mechanism that produces energy in a nuclear reactor, in which this reaction is commanded to keep it working without snowballing. The constant heat produced when the reactor is in operation is used to heat water that turns into steam and powers electricity generators, turbines. As a power source, nuclear fission has its advantages compared to fossil fuels, or various kinds of renewable energy sources. It is very compact relative to the power it can provide. A single reactor or a nuclear plant, which often has several reactors, can provide electricity to millions of homes. It also emits no greenhouse gases, unlike coal, oil, or gas, and its production is fairly reliable over time. It can work day and night and is not dependent on winds, the intensity of sunlight, or the accumulation of water reserves behind a dam, like hydropower. But its biggest flaw is the radioactive material it uses and the radioactive waste it produces. If there is an accident in a power plant working with gas, it can be bad, but it remains localized. However, a nuclear reactor with highly radioactive material in its core can be a major hazard if an accident happens and there is a breach of containment. And the problem doesn't end with the reactor. Once the nuclear fuel has been used, it becomes waste. These used nuclear materials must be monitored for years. First in pools where they are kept underground while cooling down, and then they must be stored somewhere underground. Because some of this nuclear waste will remain dangerously radioactive for hundreds of thousands of years. Nuclear plants and spent fuel tanks are operated with many precautions. There are security measures and containment systems, but disastrous accidents have still happened in the past. You obviously know about Chernobyl and more recently, Fukushima in Japan. And even without accidents, the production of very long-lived radioactive waste that future generations will have to deal with is both a hazard and a moral dilemma. So basically, nuclear energy without radioactivity and waste would be fantastic. It would eliminate all the main problems raised by nuclear plants since their appearance in the 20th century. And this is the promise of nuclear fusion, and the reason why it has been a topic of interest for decades. It could theoretically be a source of energy that uses no unstable elements for fuel, creates no dangerous waste, and is even more powerful than nuclear fission, which would make it very cost-effective. It sounds promising, and it is an exciting prospect for humanity, but it is not that simple. I will explain why, how this power source works, how it could be harnessed, and why it is technically so difficult. So to begin with, what is nuclear fusion? It is a reaction in which two or more atomic nuclei combine to form a single nucleus. In other words, it is the merging of atoms. Atoms consist of different particles. In their nuclei, there are neutrons and protons, with the key difference being that protons are electrically charged, while neutrons are not. Around these nuclei, there are one or several electrons, which have an electric charge opposite to that of protons. Typically, an atom has an equal number of protons and electrons, making it electronically neutral, unless electrons are missing. Although atoms comprise smaller particles, They are considered a relevant unit of matter for two main reasons. First, they define each element based on how these particles combine and in what quantities. Whether combining protons, neutrons, and electrons, you get different elements with distinct properties. Atoms of hydrogen, iron, copper, gold, or carbon are all made of the same basic building blocks. However, it is their quantity and arrangement that give them different properties. This makes the atomic level particularity relevant to physics, chemistry, and more generally, the understanding of properties of matter. The second reason atoms are relevant is that most atoms around us, whether on our planet or other planets in the solar system, are highly stable. They maintain the same structure over extended periods because it requires extreme conditions to break or alter an atom nucleus. With considerable certainty, I can safely tell you that almost all atoms in your body have existed for billions of years. While they may not have been combined in the same molecules, but as atoms, they already existed during the early stages of our solar system's formation, except within stars like our Sun, which we will discuss extensively in a minute. Atoms generally don't change. The only exception on our planet is a few large atoms that are naturally unstable and experience decay. They undergo fission naturally because their nuclei are formed with a number of neutrons that makes them prone to breaking apart. But this represents a very small share of matter on Earth. Other than that, atoms exist for very long periods of time. But this raises a question. Why do atoms exist? Why do the particles, the components of atoms, stick together and so firmly instead of flying past each other? It is important to understand this to grasp what happens in a fusion reaction. There are basically two forces that keep atoms together. The first one has to do with electric charge. As mentioned earlier, protons in the nucleus have a small electric charge marked as positive, and electrons have a negative charge. This is what binds the nucleus and its electrons. Opposite charges attract each other, while similar electric charges have the opposite effect. They repel. As a result, a nucleus which is positively charged will attract electrons that swarm around it. This is the first force that keeps atoms together, the one that binds electrons to a nucleus. But this raises a common sense question. If electrons are attracted by the nucleus, why don't they just merge with it or collapse into it? We may ask this question because of how atoms have been generally represented since the 19th century. The typical picture of an atom is like a mini solar system, with electrons orbiting around a nucleus, similar to how planets orbit around a star, but on a very, very small scale. Based on this representation that still dominated physics a century ago, the first hypothesis was that electrons kept separate from the nucleus because of centrifugal force. If they revolved very fast around the nucleus, then it made sense that they wouldn't fall into it, because this centrifugal force would maintain a distance. In this hypothesis, the orbit of the electron around the nucleus would have been the product of an equilibrium between the electric attraction, the force that pulls the electrons towards the nucleus, and the centrifugal force that pushed it away. This could work, but only if we accept the representation of an atom as a tiny solar system. But what modern physics tells us that this representation is not accurate. It became apparent in the 1920s that a tiny object, such as an electron, could not be treated as a classical particle with a definite position and velocity. This is the realm of quantum physics, and at this scale, we cannot always know where an electron is. We can only observe its manifestation occasionally. The electron doesn't follow an orbit around the nucleus. Rather, it manifests itself near or even sometimes inside the nucleus. This is not our topic tonight, but just bear in mind that the traditional image of electrons orbiting around the nucleus is something that modern physics no longer validates. It is still useful to picture an atom to understand its interactions, but a better image would be of a nucleus with a kind of cloud around it. This cloud represents all the locations where electrons are likely to be at any given time if we observe them. This is difficult to picture mentally, which is probably why the old atomic model with electrons in orbit still endures. This was just a tangent to explain why the idea of electrons falling into the nucleus because of electric charge attraction doesn't really have a basis. It is more of a false problem created by our traditional representation of atoms. For the topic we discussed today, let's just bear in mind that the first force that holds atoms together is the electric charge that binds electrons to the protons contained in the nucleus. But at this point, you could tell me that we have a problem. If opposite electric charges attract and similar charges repel, then the nucleus should not exist. It should explode, because it contains protons that have the similar positive charge. Why do these particles with a similar charge stick together? Because there is a second force at play, one that is stronger at this scale and more than compensates for the electric force. Moreover, the closer charged particles are, the stronger the electric repulsion is. This is why this force that keeps protons and neutrons together in the nucleus has been called the strong force or strong nuclear interaction. It was identified in the 1970s, not that long ago, as one of the fundamental forces of physics. What is a fundamental force or a fundamental interaction? There are existing forces that do not appear to be reducible to more basic interactions. We can observe them, measure them, anticipate their effects, but they cannot, in the current state of science, be explained by another interaction behind them. 4 of these fundamental forces have been identified until now, and we just talked about 2 of them. We talked about electromagnetism, which is at play in the attraction between protons and electrons that keep electrons bound to atoms. We know this force is there. We can explain and measure how it works, but we cannot go much further and understand why, at least until now. It is the same for the second force we just talked about, the strong nuclear interaction that holds nuclei together. It also holds individual particles like protons and neutrons together because they are made of even smaller particles, and we know a bit about the how. This force is carried by subatomic particles called gluons and mesons. But the question of the why, or if there is another interaction behind it, remains unanswered. The strong nuclear force works on a very small scale, a very small range, the scale of nuclei or individual particles. But at this range, it is very, very powerful. At a range of about the radius of a proton or a neutron, it is more than 100 times stronger than electromagnetism, which is why it easily compensates for the mutual repulsion of protons due to their similar electric charges and holds the nucleus together firmly. There are two more fundamental interactions. Another that exists at a subatomic scale too has been called the weak nuclear force or weak interaction. Its range is even shorter than the strong interaction. It acts inside particles, and it is the hardest to understand. We don't need to go too far in that direction tonight, but let's keep in mind that the weak force is an interaction that exists inside the components of atoms. It doesn't bind them together, but plays a role in their transformation. For example, a proton can become a neutron. It can lose its electric charge. The weak force is important in processes of decay inside atoms, which come with the emission of radiation. So, it is a third force and the fourth fundamental force, which manifests itself on a much larger scale, is gravitation. This is probably the one we are most familiar with. It not only keeps together star systems or planets, it is also what gives us weight, makes objects fall. Here again, theories have explored gravitation. They have helped measure and define it better. For example, Einstein's theory of relativity defined gravitation. But even though this theory of relativity shed new light on gravitation, it explains how it works, but does not offer another more basic interaction that would be behind it. This is why gravitation is considered a fundamental force too. Now this list of four, electromagnetism, strong interaction, weak interaction, and gravitation, is not necessarily closed. Maybe a fifth one will be added to the list one day. Some physicists think there could be yet another one, or the list could shrink. Maybe two or more of these fundamental forces could be the product of the same basic interaction that has not been understood yet. One of the goals of physics, the discipline that is still out of reach today, is to try to unify them, to understand why they exist, possibly as different manifestations of yet to discover interactions. It will certainly never solve the ultimate why. If we discover another more basic interaction behind them, we still won't have an explanation of why this other force exists. This is the field of metaphysics, what is above or beyond physics. But it would be fascinating and possibly have applications to unify some or all of these fundamental forces in a theory one day, if this is possible. So, now that we have seen more about why atoms hold together and what they are made of, let's return to fusion and try to answer this question. Why would the fusion of two nuclei liberate or consume energy? Because after all, why would combining two things together release anything? We have seen that nucleus, that is to say protons and neutrons, are held together by the strong nuclear force. This is key to understanding what happens when nuclei merge. We know since Einstein's theories that in physics, matter, a mass, a quantity, energy, which is to say the property that must be transferred to or applied to a body to perform work on it or heat it, are not entirely separate things. They are manifestations of the same thing. This defies our conventional imagination and sensible experience. But matter and energy are the same thing. Hence the famous equation E, energy, is equal to m, mass, multiplied by the square of the speed of light. E equals mc squared. Let's keep in mind that if mass increases, then energy has been consumed, absorbed, and if mass decreases, then energy has been liberated. What does this tell us about atomic nuclei? Theoretically, if you take several independent particles and they form an atomic nucleus bound by strong nuclear force, then a form of energy that wasn't present when the particles were separated has appeared and now binds them. The particles were not bound before, but now they are. This work of binding them together is energy. But energy cannot appear out of nowhere. So where was it before? It was in the mass, in the matter. This leads to the following observation that sounds counterintuitive, but has been verified long ago. When you put particles together to form a nucleus, the mass of this nucleus is less than the sum of the masses of the individual particles, because a little bit of their mass has been converted to energy. This energy is called nuclear binding energy, and it is one of the applications of the E equals mc squared equation. If you know the measure of this energy, you can use the equation to calculate how much mass has disappeared, and vice versa. Knowing how much mass has disappeared, you can calculate the energy liberated. It also means that to disassemble a nucleus into separate protons and neutrons, one needs to apply at least as much energy as the nuclear binding energy, the one that keeps it together. The loss of mass when the nucleus formed represents the energy that was released at the time of formation. This connection, this equivalence between mass and energy, is the reason why energy may be released or sometimes consumed, as we will see later, when atom nuclei change size and composition. This is why fission in a nuclear reactor releases energy. When a heavy nucleus undergoes fission into two lighter ones, less binding energy is required, and so the difference is liberated as heat and radiation. More specifically, in the case of a fission reaction, this excess energy is emitted as gamma rays, electromagnetic radiation, and also as kinetic energy. That is the movement and velocity of particles ejected from the nucleus. In fusion, when nuclei merge instead of undergoing fission, there is also a variation in the quantity of binding energy required. If it is less, then the difference is liberated, released. Sometimes it can be more. Fusion may require more binding energy for the new nucleus to hold together, in which case the fusion reaction has a negative energy balance. One has to give energy to the particles, and in that case, the reaction is called endothermic, whereas when it liberates energy, it is called exothermic. Now, if we want to harvest energy from nuclear fusion, we need to combine nuclei that will need less energy when put together into a heavier nucleus, a heavier element. But what makes the difference between fusion reactions that liberate energy and the ones that consume it? The size and structure of the nuclei are key. Typically, the fusion of light, small nuclei, elements that are the first ones in the periodic table of elements, like hydrogen or helium, liberates a lot of free energy. The most common type of fusion reaction in a star like the Sun is the fusion of hydrogen nuclei, the most abundant type of hydrogen atoms in the universe. More than 99% of hydrogen only has one proton and no neutron. So basically, an isolated proton is a hydrogen nucleus. When hydrogen atoms only have one proton as a nucleus, they are called protium. But as you know, there are variants of atoms. Sometimes they can have additional neutrons in their nucleus. These variants are called isotopes. And hydrogen has one which is less common than protium, but still fairly abundant in the universe, called deuterium. Its nucleus contains one proton and one neutron. There is another isotope called tritium, which has one proton and two neutrons as a nucleus. So when you put together two such nuclei, let's take, for example, two isolated protons, the most simple kind of nuclei, you get a more massive nucleus. But as we have seen, it is not as massive as the sum of the two protons, because a part of their mass has turned to energy. In practice, inside a star where this reaction takes place, neutrons are added to the mix. It is not just two protons. The fusion of two hydrogen nuclei can produce various isotopes of helium, the element immediately following hydrogen in the periodic table. because it has 2 protons in its nucleus. Helium with 2 protons and 0 neutrons is highly unstable and will quickly break apart. However, helium-3 or helium-4, containing 3 or 4 particles in the nucleus, 2 protons plus 1 or 2 neutrons respectively, are very stable. The 2 continuous fusion reactions occurring in a star power it by liberating enormous amounts of energy through radiation, heat, and particles with kinetic energy. During most of its lifetime, a star sustains itself through the fusion of light atoms, primarily hydrogen, and to a lesser extent helium, creating heavier nuclei. However, it cannot produce the heaviest elements because, as mentioned earlier, these require an absorption of energy. Their creation costs energy rather than releasing it. The limit in the list of elements where fusion begins to require an input of energy is an isotope of iron called iron 56, which has 56 particles, protons, and neutrons in its nucleus. The creation of elements heavier than iron 56 via fusion reactions is endothermic, meaning it consumes energy instead of releasing it. And for that reason, it is believed that the appearance of these heavier elements takes place in the last phases of a star's life, when it has exhausted a large part of its available hydrogen and dies. It ends in an explosion, a supernova, followed by a collapse. The energy released in a fraction of seconds at that moment is so gigantic that heavy nuclei fuse by absorbing some of this energy. But what is important to understand here is that to harvest energy from a fusion reaction, you need to make protons come closer enough to each other so that the strong nuclear force, which is very powerful but has a very short range, can come into play and overcome the repulsion between the protons that is due to their electric charges. Before they are close enough, they repel each other, and this natural repulsion needs to be overcome by giving them enough energy so they can overcome the electromagnetic force. In other words, to harvest energy from fusion, you need to spend energy first, and then, when fusion happens, you will get back more than what you spent. But there cannot be fusion without an already intensely energetic environment. This is why it happens in stars when heat and pressure conditions are extreme due to gravitational forces. The star is a very large and massive body. The forces inside defy imagination. But in space, in the void, on planets, fusion cannot occur naturally. This is a big difference with fission energy. Fission happens because of the natural instability of nuclei. It occurs naturally on Earth, which is why there is a low-level natural radioactivity around us all the time. In a nuclear reactor, we put a lot of fission-prone or fissile material together, and then we start and pilot our reaction. We don't need to give it energy for the fission reaction to begin. Fusion is much, much harder to ignite. It is theoretically conceivable to make it self-sustaining. Once fusion reactions begin inside a closed, contained space, they can liberate energy that will allow more reactions to happen. But the ignition costs energy. A challenge in turning fusion into a power source is to create an environment inside a reactor where fusion happens continuously, and the energy it liberates allows more fusion reactions to take place, so that the energy balance is positive. And this is the technical challenge we are now going to discuss: how to create a confined reactor inside which temperatures are somewhat similar to the inside of a star. In reality, even higher, because inside a star there is very high pressure due to gravitation that cannot exist inside a reactor. So the temperature needs to be pushed even higher. We are talking about more than 100 million degrees. That is a temperature that can quickly melt any material we know of. But this incredibly high heat needs to be confined inside the reactor. And on top of that, we need ways of extracting the energy liberated by fusion. This is the extraordinarily complex engineering challenge raised by fusion power. Inside a star, a long-lasting fusion reaction can exist because gravitation provides confinement. The star is held together by gravitation. It is very large, so reactions can take place inside stars, and yet they do not explode or dissipate in space because gravitation pulls all their components towards the center. For artificial fusion to be viable, we would need to recreate these conditions. But obviously, gravitation cannot provide confinement because it would be on a much smaller scale. In a nuclear reactor, this problem does not exist because there is no requirement for high temperatures and pressure for fission to occur. So a tank filled with water and rods of fissile material of fuel is sufficient, provided the heat from the reaction is evacuated constantly. This is how we harvest calorific energy in such a reactor. The tank will not melt because the temperature of the water inside does not go above a few hundred degrees. The temperature necessary inside a fusion reactor is on a completely different scale. At the points where fusion reactions take place, it is more than 100 million degrees, even though this doesn't touch the walls of the reactor. These walls would have to withstand extremely high temperatures. The constraints are challenging, to say the least. This is why, from the moment artificial fusion as a source of power began to be researched in the 1950s, the idea of confining the reaction inside a magnetic field emerged. But what does this mean exactly? First, we need to talk about what needs to be confined and what happens to matter when it is exposed to extremely high temperatures. Matter in such an environment turns into plasma. But what is plasma? Generally, we learn in school that matter has three fundamental states: solid, liquid, and gas. The understanding of this in the 18th and 19th centuries was an advance in modern physics and chemistry, and these categories remain useful because, indeed, this is how we encounter matter on Earth in our daily lives. Assuming we are at sea level, pressure on Earth, if you take a solid and heat it, it will turn into liquid. And if you heat it more, it will become a gas. But these three states do not really grasp the entire spectrum of states of matter. For example, recently I told you about supercritical fluids in a story about astronomy. The atmosphere near the surface of Venus, or the layers inside gas giants like Jupiter, would be in that state that is neither liquid nor gas. There is another state called plasma, and even though we naturally encounter it rarely on Earth, it is actually by far the most abundant state of matter in the solar system, and also probably in the universe, because this is the state of most of the matter inside stars. And the Sun, just to take our solar system as an example, accounts for more than 99% of all matter in the solar system. Plasma is what you get when you superheat a gas so hot that the electrons are ripped away from the atoms, forming what is called an ionized gas. Ionized because ions are particles, atoms with a positive electric charge. A proton alone or an atom alone that misses an electron are ions. Taken as a whole, plasma does not necessarily have a positive or negative electric charge because the charges of its particles compensate each other, as long as it contains as many electrons as ions. But the plasma requires different properties, and the most important is that it becomes electrically conductive. It reacts to magnetic fields because this cloud, this soup of particles, will move collectively due to its electric conductivity. Now, the concept of plasma in everyday language is somewhat blurred because there is no exact definition of the transition point between gas and plasma. There are applications like neon lighting or plasma screens, though these have largely disappeared now, having been replaced with other technologies like LCDs. But these were applications that used plasma, and obviously a neon bulb or a plasma television do not warm up to thousands of degrees. This is because they contain gas that is only partially ionized. It is not pure plasma, but it still has specific properties that can be utilized when powered by electricity. Ionization exists on a spectrum. It can affect only a few particles or all of them. The plasma we find inside a star or inside a fusion reactor is fully ionized. It is so energetic that atoms have been stripped of all their electrons, leaving only bare nuclei. This is what is needed for fusion to occur inside plasma. It creates a soup or hot cloud of nuclei and free electrons within which the now positively charged nuclei are energetic enough, very hot and very fast, that they can collide despite their electric repulsion. They have the same electric charge, as you may recall. They can come close enough for the strong nuclear force to overcome their electromagnetic repulsion and fuse into heavier nuclei. The elements, the fuel, that can be used are very important here because, as we have seen before, only fusion of small nuclei releases energy. These reactions are called exothermic as opposed to endothermic reactions, which consume energy. The best possible fuel is hydrogen because, first, it is the lightest possible nucleus. Second, it has only one electron. so it is easier and requires less temperature and energy to ionize it, to rip the single electron off from each atom and turn it into an ion. The confinement of a plasma heated to more than 100 million degrees is inconceivable with walls, as they would immediately melt. But as we have seen before, plasmas are electrically conductive and can be controlled with magnetic fields. Possible designs of fusion reactors take advantage of this to confine the particles as they are heated. While the plasma cannot touch the reactor walls, but what if we control the plasma in suspension with magnetic fields so that it doesn't make contact? This idea, which is also a necessity, forms the basis for all fusion reactor designs, including the most famous one called the Tokamak. Tokamak is a Russian acronym that has been adopted by other languages. The name comes from Russian because this type of device was conceptualized in the 1950s by Soviet physicists. For the record, one of them was Andrei Sakharov, who later became famous for being a dissident of the Soviet regime and a human rights activist. So the tokamak is only one of several types of magnetic confinement devices that were and continue to be developed to produce fusion power. If one day we manage to have a functioning fusion reactor, that is to say with a positive energy output, it will not necessarily be a tokamak. However, it is one of the best, if not the best candidate. The inside of a tokamak looks like a ring, and it is designed to contain plasma in the shape of a torus, which is the technical term for a donut shape, a thick disc with a hole in the middle. Why a donut? Because it is an optimal shape. Having magnetic lines that wind around the torus strongly helps to stabilize and keep the plasma in place. Other types of designs have been conceived both before and after the tokamak. They are called stellarators, Z-pinches, or magnetic mirrors. We won't delve further into these types of devices tonight. There are different approaches to plasma confinement with magnetic fields. They all have, or had when they were abandoned, their advantages and disadvantages. The biggest disadvantage for such systems is the loss of plasma if it doesn't stay in suspension, but instead leaks or escapes from the zone where it should be confined. You understand the complexity of this. It is necessary to make plasma that will be several million degrees hot remain in suspension, levitating inside a reactor, while at the same time, particles inside the plasma move at speeds that defy imagination. When it was invented in the 1950s, the tokamak design was a leap forward because it suppressed the instabilities that plagued earlier designs. At the end of the 1960s, tokamaks looked very promising. They had not achieved a net positive output of energy, but they had better results than any other designs, and that's why they multiplied around the world in research facilities. But then bigger and bigger devices made with the hope of reaching a positive output disappointed. They encountered new problems when they were built on a larger scale, and there were disappointments in the 1980s. The reason why the output remains negative is not that these reactors don't achieve fusion. They do. They heat plasma in suspension. This is complicated technically, but doable by inducing a powerful electric current inside the plasma. You remember the plasma is conductive. Then fusion reactions begin, and new fuel, new hydrogen, has to be introduced to keep the reactions happening. But the problem is that the heat generated by the reactions is not sufficient to make more reactions happen and make the reactor self-sustainable while simultaneously harvesting energy from it. The plasma cools down when heavier elements, products of fusion, accumulate in it. The plasma is not stable enough and leaks, so more power must be given to the reactor to make it continue working. And instead of producing a net surplus of energy, the reactor requires an input. As of today, the machine that holds the record for fusion output is the Jet European Taurus, which is located in England. Its output reaches 16 megawatts, but required an input of 24 megawatts, so it remains significantly negative. Nevertheless, progress has been made in the past decades. These performances are well above those achieved with the very first devices. Hopefully, they will keep improving with better materials, better fuel, and bigger devices too. Research continues around the world. Because it requires extremely complex engineering, expensive equipment, and large teams of scientists and technicians, some of these efforts are international. The primary international effort to advance towards a practical fusion reactor today is based on a perfected tokamak design called ITER, International Thermonuclear Experimental Reactor, a project under construction in southern France. When it opens in a few years, it should be the largest tokamak in the world and, more generally, the largest experiment for plasma containment, with 10 times the volume of any other operating tokamak today. Part of the hopes placed in this project rely partly on the change of scale to generate a net positive output. If this works, how could such a reactor harvest energy through the following process? The energy liberated by exothermic fusion comes in the form of heat and particles with kinetic energy. These particles are expelled from the new nucleus, and when these particles are neutrons, they are not bound by the magnetic fields that keep the plasma in place. Because they have no electric charge, so they are not affected by a magnetic field. Consequently, they escape the plasma and heat the reactor walls. So this mechanism, calorific energy, heat, can be extracted. Like in a fission reactor, it can be extracted by circulating fluid, water, that comes in contact with the hot walls and be used as steam to power turbines that produce electricity. If this can be achieved, the reactor would have several advantages over other energy sources. There would be no release of pollutants, as with fossil fuels, and the main products of hydrogen fusion are helium atoms, which are neither radioactive nor dangerous. There would be only marginal creation of radioactive waste, still a little bit, not because of the fusion reaction itself, but because of the absorption of neutrons by the surrounding material inside the reactor. But this is not a significant concern based on current knowledge, because these byproducts would have a short half-life quality, losing their radioactivity, and are far less toxic and dangerous than the waste products of a nuclear reactor. It is likely that we will not see a functional fusion reactor this decade, or probably neither in the next. There is very little hope that fusion reactors can solve energy issues in the short term. But however complex the engineering and difficult the task, the potential rewards justify the efforts to design one. The fuel would be cheap, as hydrogen is abundant. The hydrogen used in such a reactor would need to be processed, as it would work with hydrogen that has one neutron, deuterium, and hydrogen with two neutrons, tritium. Both isotopes, especially tritium, don't occur much naturally, so they would have to be produced, but that would still be relatively inexpensive. The cost of electricity produced by fusion would essentially be the amortization of the reactors. While they would be very costly at first, the cost of maintaining and operating them, but just the environmental promise of very low waste and no greenhouse gases is attractive. We have come to the end of our journey tonight. I hope you enjoyed this adventure, and I invite you to discover and learn more. Now you can let go and sleep. Or if you're not sleepy yet, you may pick another story from my ever-growing library. And until we meet again, good night. Sleep well.